I'll give the floor to you so you can tell us all about your project.
Okay. So, good afternoon. Thank you so much for being here. Here is a problem I was obsessed with. We have all these methods for studying how babies learn to ignore familiar things, habituation. But here's the issue. Everyone does it differently, the results don't compare, and clinically, it's almost useless. So I thought, what if we could apply mathematical modelling to make this precise and reproducible? That's what this whole project is about, using exponential decay to quantify infant brain activity in a standardised way. So first, what is visual habituation? Simply put, babies get bored. Show them the same toy over and over, and eventually they'll stop caring. Their attention drops, that's habituation. It's a brain learning, okay, I've seen this before, nothing new here, moving on. Dr. Mimroy, my supervisor, puts it brilliantly. Habituation is one of the earliest cognitive processes to emerge in development. Basically, even tiny babies can do this, and how efficiently they habituate tells us a lot about their cognitive development. Here's how we study it. Show the baby a colourful image repeatedly. That's the familiar stimulus. Baby looks, 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 then gets bored and looks away more. That's habituation happening. Then we throw in a novel stimulus, something they've never seen before. If they've truly habituated to the familiar one, they'll perk up and stare at the new thing. That's called dishabituation. When we show them the familiar one again, boredom returns. Habituation is typically measured through looking time. How long the infant fixates on a stimulus, the duration of their gaze, and how often they orientate towards it. As trials progress, if habituation is occurring, you'll see decreased looking time, reduced fixation duration, and fewer orientation responses. Basically, the baby gets progressively more bored. Now here's why it matters clinically. Babies who can't habituate is a big red flag. It suggests something isn't quite right with our central nervous system. It has been linked to all sorts of developmental risks. Okay, so why should we care about this beyond academic curiosity? Because the stakes are genuinely high. Zakard, Kras and colleagues in 2021 studied preterm babies, so babies born too early. And they found they habituated way slower than full-term babies. The culprit? Immature GABAergic systems. That's the brain's inhibitory neurons. The ones that say, okay, calm down, we've seen this before. When those systems aren't developed, babies can't filter sensory information properly. They can't tell what's familiar versus what's new. And the consequences aren't trivial. Poor habituation in newborns predicts lower IQ scores. We're talking 8 to 12 points lower on average. Plus attentional problems when they hit school age. Chung and colleagues in 2020 showed habituation metrics predict which kids will struggle with executive functioning and show ADHD traits by age 5. But here's where it gets really powerful. Tony's 2024 study looked at infants at a higher likelihood of autism. At just 6 months old, before any formal diagnosis is even possible, these babies showed reduced habituation. They took longer to get bored and couldn't discriminate between familiar and novel as well. And that 6-month deficit predicted poorer social communication skills at ages 2 and 3 and was associated with later autism diagnostic scores. Think about it. We could potentially identify developmental concerns years before diagnosis is even on the table. That's game-changing for early intervention. But here's the frustrating part. Traditional habituation research can lead to a range of methodological issues. Problem 1, stimulus preference. Oakes pointed this out in 2010. Babies have opinions. They love faces, they love complex stuff, and they love movement. So when a baby stares longer at something, are they failing to habituate, or do they just really like that toy? It's hard to tell. Problem 2. Looking time is messy. Aslan demonstrated in 2006, looking time doesn't just reflect habituation. A noisy room, a baby will look away. A tired baby, they'll look away. A bored baby also looks away. You see the issue. We're conflating genuine neural adaptation with basically everything else. And problem 3, and this is the killer. Every study does it differently. Ashmead and Davis found reliability coefficients as low as 0.3 in some habituation studies. What counts as habituation in one lab doesn't count in another. You can't compare studies, you can't build a coherent literature. Enter EEG, the brain scanning superhero we don't talk about enough. EEG is beautifully simple. We put an electrode cap on a baby's head, looks ridiculous but works brilliantly. It records electrical activity from their brain in real time. We're measuring thousands of neurons firing in sync. Why is it better than watching babies stare at things? Well, there's 3 main reasons. 1, millisecond precision. We can see habituation occurring in the brain, not just when babies look away. 2, it's completely safe. No radiation, no surgery, just a weird looking cap and some gel, which is perfect for babies. 3, temporal dynamics. Sure, fMRI has better spatial resolution. It can tell you where in the brain this phenomenon is happening. But EEG tells you when and how fast. And for habituation, timing is everything. The research backs this up. Kattis and colleagues tracked babies from ages 1 to 18 months. At 1 month, babies' brains respond to everything equally. By 5 months, they've learnt to discriminate. Their P3 brain response decreased to repetitive sounds but increased to novel ones. That's habituation happening captured in the brain. Pinto's 2022 review and Gonzalez-Frankenberger's 2008 study both confirm that EEG captures habituation beautifully through changes in brain wave amplitude. Which brings us to the star of our show. Gamma power. Electrical activity in the brain within the gamma frequency range, typically above 30 Hz, has been specifically linked to habituation processes. The foundational study here is Snyder and Keel's 2008 research. They investigated neural mechanisms of habituation in 6-month-old infants using EEG. Their work built on the temporal correlation hypothesis, which proposes that gamma oscillations solve the binding problem, the brain's ability to combine discrete features distributed across different neural populations into coherent representations. In their study, infants were randomly assigned to either a face or object condition. They found that gamma power decreased significantly over occipital regions with repeated face presentations. Critically, greater gamma suppression predicted stronger novelty preference, so longer looking at the novel stimulus, suggesting gamma suppression is functionally linked to efficient visual learning and faster habituation rates. This was the first study to link gamma habituation to behavioral novelty detection in infants. Other research has shown that gamma power can return to a baseline post-habituation. Santos Mayo and colleagues in 2022 found that gamma power decreased during habituation but returned to a baseline post-habituation, confirming this was learning dependent and not fatigue. This brings us to an important concept, the asymptote. Research by Grill-Spector and colleagues in 2005 provided evidence of repetition suppression across fMRI and EEG recordings. They found that the bold signal reduction stabilized after 6 to 8 repetitions. The authors suggested this could be due to a sharpening model, where sparse coding stabilizes, leaving only essential neurons active. This asymptote has also been demonstrated specifically in gamma power. Staunch and colleagues in 2021 investigated how repeated visual stimuli affected gamma band synchronization using MEG. They found that gamma power demonstrated a steady increase after 10 repetitions, then reached a stable baseline, so an asymptote. However, these mixed findings reveal a critical gap in the literature. There's no standardized method for accurately measuring gamma power during habituation. Typically, researchers analyze percentage changes between initial and final gamma as an indicator of habituation. But this doesn't provide the rate at which habituation occurs. This gap has real consequences. Inconsistent results can hinder assessment of pharmacological and non-pharmacological interventions. Despite research by Etheridge and colleagues in 2019 showing that elevated gamma power during habituation tasks correlated with hyperactivity and lower cognitive abilities, we can't effectively use gamma power as a biomarker without standardized quantification methods. And that is where my research comes in. So here's my solution, the exponential decay model. And I promise it's not as scary as it sounds. The equation is Pt equals P0 times e to the power of negative kt plus c. Let me break this down in human terms. Pt is just gamma power at any given trial. So if trial 2 has 1.8 microvolts squared of gamma power, that's your Pt. P0 is where you started. It's your initial gamma power at trial 1. E is Euler's number, which is about 2.71828. It's a mathematical constant, so just accept that it exists. Okay, and this is your magic number, is your decay rate. How fast is habituation happening? A larger K means faster decay, which means faster habituation. This is what we're hunting for, a single number that quantifies habituation speed. Comparable across studies, standardized, beautiful. T is time. And here's a crucial decision that I made. We timestamp each trial, not just count them. I'll dive into that deeper further on. C, as we've just discussed, is your asymptote, so the baseline gamma settles after habituation. Van der Meissen used this model in 2023 to measure pain habituation. It worked beautifully, way better than linear models. But they used pain ratings, not brain activity. So could we apply it to gamma power? That was a big unknown. That's what I wanted to test. Based on this theoretical foundation, I formulated 2 directional hypotheses. Hypothesis 1, gamma power will decrease in response to a repeated visual stimulus before stabilizing at a baseline. This is based on Snyder and Keel's 2008 findings and the broader repetition suppression literature. Hypothesis 2, gamma power will fit the exponential decay model sufficiently. Specifically, we set our threshold at r squared greater than or equal to 0.7, indicating that decay rates are an accurate measure of habituation speed. If both hypotheses were supported, it would establish exponential decay modeling as a reliable, standardized method for quantifying infant habituation rates, with significant implications for developmental assessment and early intervention. The number of participants was determined prior. For a medium effect on early versus late gamma, we needed 27 infants. For the model fit test, at least 15. We recruited 27, but after inevitable infant EEG attrition, we ended up with 15 usable data sets, aged 10 to 18 months. It's a within-subject design, so every infant saw the same habituation paradigm, and we measured gamma power on every trial. We used 2 unique, colourful images, One is a familiar stimulus, one is a novel, or as we called them in the lab, Fred and Spike. The procedure was designed to be as infant-friendly as possible. Parents and infants visited our EEG lab at Keele University. We prepared the electrode cap beforehand. When families arrived, we placed the caps on the infant's head and secured it with a chin strap. Another experiment blew bubbles during this to distract the infant and make it a more pleasant experience. An attention grabber was played first to orientate their gaze towards the screen. Then we presented either stimulus A or B repeatedly, whichever was designated as familiar, for a maximum of 100 trials or until habituation occurred. The novel stimulus was presented during the dishabituation phase. We recorded videos of the infants to identify trials in which they weren't paying attention, and we later removed those trials from the analysis. This gaze data was coded frame by frame and double-coded to verify reliability. Importantly, for infants classified as inattentive, an auditory attention grabber was used at the start of each trial. This turned out to be quite significant in our exploratory analysis. For EEG pre-processing, we used MATLAB with the field trip toolbox. Steps included artifact removal, baseline correction, re-referencing and filtering. We suppressed line noise at 50 Hz and manually rejected artifacts, on average 21 trials per infant. We removed and then interpolated noisy channels, on average 8 channels per infant. We filtered data to isolate gamma activity between 30 and 50 Hz using a 0.5 second time window. And we focused on the occipital electrodes, the O1, the OZ, and O2, as they're optimally suited to capture visual cortex activity. For the modelling, we extracted gamma power from each trial and fitted it to the exponential decay function I showed you earlier. We used Excel's nonlinear solver to calculate K, the decay rate, and R squared, the goodness of fit. We defined initial parameters, calculated predicted gamma power using our formula, computed squared errors between actual and predicted values, and then used solver to minimize these errors and determine the actual K value. The R squared value then indicated how well the data fitted the model. As I previously mentioned, a critical decision we made was to timestamp rather than use trial numbering. In infant research, we commonly remove noisy trials from data. If you use trial numbers, you assume fixed inter-trial intervals. But in our study, they vary between 1.2 and 1.5 seconds. Additionally, if you just use trials 1, 2, 3, so on, you assume an equal spacing. But trial 3 might be 10 seconds after trial 2 because you excluded 3 trials in between due to look-away rates. Trial numbering could also potentially overestimate the K when trials are removed, creating uneven pacing. Timestamping allowed us to reconstruct the actual temporal sequence, maintaining temporal integrity, a component both exponential decay and habituation paradigms require. Hypothesis 1 was that gamma power would go down over time as infants habituated. Early trials, the mean gamma was 2.16 microvolts squared. Late trials, 2.25 microvolts squared. So if anything, it went slightly up. The paired t-test gave a p-value of 0.72. I'll be honest, this is not what I was expecting. We accept a null hypothesis. Gamma power did not decrease during repeated stimulus presentations in our sample. Hypothesis 2 was that the exponential decay would fit well, with R squared equal to or greater than 0.7. Instead, the mean R squared value was negative 4.6. Statistically, it was significantly below our threshold. In other words, the model didn't just fit badly, it failed in a spectacularly obvious way. On paper, this looks like a disaster. My entire study premise just crashed and burned. Okay, so I need to address the elephant in the room, the negative r² value. That sounds wrong. Most people have been taught r² must be between 0 and 1. So what's happening here? r² is only bound between 0 and 1 for ordinary least squares linear regression. For nonlinear models, a negative r² is mathematically valid. It simply means the model fit the data worse than a horizontal mean line, which in itself is an important finding about whether exponential decay applies to this data at all. Let me break down why the 0 to 1 rule exists in linear regression and why it breaks down in our study. SSE is the sum of squared errors. How wrong your model's predictions are versus the actual gamma power values. SST is the total sum of squares. How much the actual gamma values vary around their own mean. In ordinary least squares linear regression, the maths guarantees the model will always explain at least as much variance as the mean alone. So the sum of squared errors can never exceed the total sum of squares, keeping r² equal to or greater than 0. Our formula is r² equals 1 take away the sum of squared errors divided by the total sum of squares. For r² to be positive, your model needs to be better at predicting the data than simply guessing the mean every time. When r² equals 0, your model is no better than the mean. When r² is negative, your model is actually worse than just using the mean. It introduces more error than it removes. So why does this break down in our study? We use a nonlinear model. The exponential decay function, pt equals p0 times e to the negative kt plus c. This is not linear regression. Excel's GRG nonlinear solver doesn't carry the same mathematical guarantee. It finds the best it can, but that best can still be worse than the mean. Our data doesn't follow the assumed shape. If the underlying data has no systematic decay, the model is essentially being forced onto a pattern that just isn't there. The predictions can end up further from the actual values than the mean would be. Let me show you what's happening in our Excel model looking directly at the data. The numbers tell a clear story. So this is from one of our participants. So total squared errors between our predicted and actual gamma values here is 4.248. The total variance in the actual gamma data is equal to 1.88. So using our formula, it would be 1 take away 4.25 divided by 1.88, which is equal to negative 1.26. The sum of squared errors is more than twice the size as the total sum of squares. This means that the model's predictions are further from the actual values than the data is from its own mean. So the model is actively making things worse. This is a really common misconception that r² must be between 0 and 1. But that rule is only true for standard linear regression with an intercept. It's a specialized case, not a universal law. But wait, because here's where this project transforms from sad failure to actually really interesting findings. Remember how I mentioned some babies had an auditory attention grabber? A little sound to keep them focused. I got curious. Does that actually change anything? So, we split the babies into two groups. Infants with no audio versus infants with audio. Then compared their model fit, so those r² values. The results were statistically significant. The audio condition showed significantly better model fit than the no audio condition. So what's happening here? Multisensory integration. When babies get both auditory and visual inputs together, it fundamentally changes how their visual cortex processes information. This aligns perfectly with COP's 2014 work on audio-visual integration. Here's my interpretation of it. The auditory stimulus triggers gamma phase resetting in the visual cortex. There are direct neural pathways, thalamocortical projections, that let sound influence vision processing. When you pair audio and visual stimuli, you're synchronizing neural activity between auditory and visual brain regions. That synchronization creates more organized, systematic patterns of gamma decay. It's like if I got everyone in this room to clap visuals only, it'd be very unlikely that everyone would be clapping together. If you add an auditory beat, suddenly everyone's synchronized. It's a similar principle in the brain. Following this, I asked another question. Does auditory stimulation affect the magnitude of gamma power itself, or just its temporal organization? Conducted another independent samples t-test comparing mean gamma power between the audio and no audio conditions. The no audio group showed higher average gamma power, 3.3 microvolts squared, compared to the audio group at 1.5 microvolts squared. That's a substantial mean difference of 1.8 microvolts squared. However, the Welch's t-test, which was used because the groups had unequal variance, indicated that the difference was not statistically significant. This is a profound finding. It demonstrates that auditory inputs modulate the temporal trajectory of gamma power without fundamentally altering its amplitude overall. This association suggests that cross-modal influences operate primarily through phase resetting mechanisms rather than controlling population-level excitatory activity. Research by Mercer and colleagues in 2013 supports this. They found that auditory inputs can reset the phase of ongoing visual cortex activity without changing power spectral density. The brain reorganizes temporal coordination while preserving overall excitatory-inhibitory balance. Okay, so why didn't we find gamma power reduction like Snyder and Keel in 2008? Reason 1 could be stimulus type. Snyder and Keel used faces. We used geometric patterns. That matters enormously. Human brains are obsessed with faces from birth. There's literally a specialized region called the fusiform face area just for faces. In contrast, the geometric patterns used here likely relied more strongly on early visual areas, such as the V1 and V2, and less on specialized face selective circuitry, which could contribute to the observed sustained gamma synchrony, although the precise microunit mechanisms remain to be determined. Reason 2 could be developmental timing. We think the age difference helps explain why Snyder and Keel saw gamma suppression at 6 months, but we didn't at 10 to 18 months. At 6 months, long-range frontovisual connections are still relatively immature and weakly myelinated, so gamma likely reflects most local bottom-up visual processing. By 10 to 18 months, myelination and connectivity between frontal and visual regions have advanced, supporting stronger top-down attentional control of visual cortex. From this perspective, our stable gamma may indicate more efficient, well-regulated processing in a more mature network. In reason 3, the embarrassingly simple explanation, trial count. We averaged 16 trials per infant. Snyder and Keel, 59 trials. We might not have captured enough data to see the effect. Habituation takes time to stabilize, so 16 trials might not have been enough. The failure of the exponential decay model highlights the limitation of applying mathematical models to the development of neural activity. The negative R² value indicates the exponential decay model may not universally capture the complexity of neural habituation in early development, particularly when using gamma power. This contrasts with previous research that successfully applied exponential modelling to habituation mirrors, but those focus on self-reported scales rather than neural biomarkers. The failure could be due to including the term C, the asymptote, in our model. Perhaps in this developmental context, neural gamma doesn't stabilize at a constant baseline as assumed. So C, the asymptote, also acts as a force floor for the model, meaning the model cannot move freely or adjust to the data. Or, more fundamentally, without gamma power reducing, the model simply cannot fit. This calls for a critical examination of modelling applicability in infant EEG research and suggests that more nuanced models may be required. Perhaps tri-exponential decay models that account for faster fusion components, or hybrid models that combine decay parameters with cross-frequency coupling metrics. Despite the null findings, the data have important theoretical implications. Classic accounts treat habituation as mainly synaptic depression, so less neurotransmitter released at the same synapse. But that kind of local mechanism doesn't naturally explain why, in our cross-sensory condition, gamma amplitude is preserved while the timing becomes more organized. This pattern suggests additional network-level processes that maintain excitatory-inhibitory balance, but reshape the temporal trajectory of gamma, especially when audio and visual input are combined. Second, our findings challenge the notion that habituation is a unitary process. Instead, they propose a dual component system where temporal trajectory and overall amplitude excitability are independently regulated. Simply put, this suggests that gamma has at least two partially independent components: how strong it is, so the amplitude, and how it evolves over time, so the trajectory. Audio doesn't really change the overall gamma level, but it makes its time course more structured. So habituation isn't just more or less gamma, it's also about how gamma is organized. Third, the findings redefine the development of biomarkers for neurodevelopmental disorders. While mean gamma power demonstrate poor reliability due to high inter-individual variability, the multisensory paradigm enhanced model fit. This suggests that if we use multisensory habituation paradigms, combining auditory and visual stimuli, we might get more reliable, systematic gamma trajectories that could serve as a robust biomarker for tracking intervention efficiency. Essentially, we could monitor whether therapeutic interventions are normalizing neural adaptation by observing whether gamma power trajectories improve over time. For autism spectrum disorder and Fragile X syndrome interventions, the implications could be more profound. Our findings indicate that structured audiovisual stimulation during critical developmental stages could improve cross-modal phase synchronization. What does this mean in plain English? It's essentially teaching the brain to better coordinate its internal rhythms for processing sights and sounds together. Why does this matter? Many individuals with autism spectrum disorder and Fragile X syndrome experience sensory hypersensitivity. They're overwhelmed by sensory input because their brain struggles to filter and integrate information efficiently. If we can train the brain early on to synchronize auditory and visual processing through structured multisensory habituation tasks, we might mitigate that overstimulation before it becomes entrenched. We're talking about potential early intervention strategies that could reduce sensory overwhelm and improve quality of life. I want to be transparent about this study's limitations. Our average trial count of 16 was substantially lower than that in comparable studies. We may have missed critical habituation gamma dynamics. Our stimuli were also geometric patterns rather than ecologically valid social stimuli, which might not engage the same neural networks as faces or social scenes. Future research should prioritise several directions. First, expand sample sizes substantially and extend to neurodevelopmental risk groups. Second, use multisensory habituation paradigms, which enhance ecological validity. Dynamic faces paired with concurrent vocalizations to better engage developing face processing networks. Third, integrate more specialized modeling, such as tri-exponential decay models. And fourth, utilize longitudinal designs over crucial developmental years. Additionally, use hybrid models that combine decay parameters with cross-frequency coupling metrics, such as gamma-theta interactions, and investigate whether structured auditory visual training, such as during sensitive developmental periods, can enhance cross-modal synchronization in at-risk populations. So let me wrap this up by telling you what this study achieved, despite the null results, or maybe because of them. Here's the big takeaway. Gamma power magnitude and temporal dynamics seem to be independently regulated. They don't move together. Auditory input doesn't change how much gamma you have, it changes how it's organized over time. That's fundamentally important and challenges everything we thought about habituation being purely amplitude-based. The multisensory findings is a real gold here. When babies receive auditory and visual input together, the brain activity becomes much more organized and predictable. This supports predictive coding frameworks and indicates that we need multimodal biomarkers for neurodevelopmental assessment. Not just is gamma high or low, but how does gamma change over time across sensory modalities? Clinically, this could open doors. Structured audiovisual interventions during critical developmental windows could potentially help at-risk populations by improving cross-modal synchronization. We're talking about training the brain to better coordinate sensory processing. That could mitigate sensory hypersensitivity issues down the line. Methodologically, this proves something important. Modeling neural data reveals patterns you'd completely miss with traditional amplitude-only approaches. Null findings aren't failures, they're information. They tell you where your assumptions were wrong and point you towards what's happening. There are some of the key contributions of this research. It's references. Thank you.